So in part 2 of lab, what have we done? Well, in summary, we've computed these 4 measures. We've determined in MATLAB how to take our adjacency matrix and compute things like the total number of edges, the average degree, the average clustering coefficient, and the average path length. And these 4 numbers provide a simple numeric summary, a 4-number summary of a very complicated or potentially complicated network structures. So far we've looked at a simple network. What I'd like to do in the last part 3, is analyze some real data of macaque cortex. So this is monkey cortex. And what we'll do is we'll download this data set from Blackboard Learn. So if you go to Blackboard Learn for this week, you can define, or you can find this variable, macaque.mat, and then we can load it into MATLAB. And that's what I'll do here. I'll load this data set into MATLAB, and we can start immediately asking questions about it. First, what happens when we load in this data? I've navigated to the right directory, so I don't get any errors here. I see it loads in 2 things. It loads in this variable A, which is 71 by 71. This corresponds to the adjacency matrix, which specifies the structure of the network. And then there's also this variable names, which corresponds to the names of the nodes in this network, in case you're interested in looking at that. And we can start immediately asking questions. For example, how many nodes are in this network? We see that the adjacency matrix is 71 by 71. So in this case, it has 71 nodes. Each of these nodes corresponds to a cortical region. We've simplified this data set a bit by making it symmetric. It's not actually symmetric, it's pretty close, but we've made this simplification so we could apply some of our tools and see how it behaves. So what we can do to start is let's try to visualize this data set, and the way we can do that is by issuing this spy command like we used earlier. So if I say spy A, here is the adjacency matrix, and again this represents the connectivity of this monkey cortex. We have 71 nodes by 71 nodes, and each dot here indicates a connection between nodes. So you can get some sense for the connectivity. It's not completely blue, so everything is not connected to everything else. It's not completely white, so we do have some edges here. And maybe we can get some sense for its structure. And again, what we can do is we can compute all of the measures we've considered so far. So what can we do? Well, we can compute things like the total number of edges. How do we do that? Well, we said we could sum A, comma 1 and sum A, comma 2. So we're going to sum up all rows, all columns, and then divide by 2. And we get 438 edges in this case in our network. We can compute things like the average degree, and how do we do that? Well, we can scroll up in our code and figure out how do we compute the degree. If I hit degree and up arrow, we can sum up our matrix, our adjacency matrix A along the second dimension, and then compute the average degree. How do we do that? Well, we take the mean of degree. So we can compute the average degree, and let's have a look. What does that equal? The average degree. 12.3, so we find the average degree of 12.3 in this case. So each node connects to approximately 12 other nodes. And we can do things like compute the average clustering coefficient. If I scroll up in our code, we can look for the lines where we compute the average clustering coefficient. We can use the exact same operations, so I'll copy this line, 166. Now we've defined the adjacency matrix A to correspond to this monkey cortex. So if we compute the clustering coefficient here, we can then compute the average clustering coefficient, again using the same code as above. And we can look and see what is the average clustering coefficient, near 0.5 in this case. And we can compute the average path length. We can use this distance command again, or we're using that command distance binary, which we downloaded from the web. We compute the distance matrix, and here it is. And if we look, what is the size of distance? It's 71 by 71 again, specifying the paths between each pair of nodes. And we can compute the average path length, where in this case we have to set n equals 71 because we have 71 nodes in our network, and we want to make sure we scale by the correct value. And then we can compute the average path length, and let's have a look. I've just pasted in this line, in this case 222, into the MATLAB command prompt, and we find an average distance of 2.2. So in this way, we're able to compute all of these 4 numbers, this 4-number numeric summary for this data set, which actually corresponds to anatomical connectivity in a real brain.